Okay. Oh, good morning. Good morning, just in time. So let's start this lesson, in which I will try to provide you a short introduction to ray optics. I'm sure that most of you have already been exposed to something about ray optics. In this course, I have decided to address this topic because it's a nice application of the theory we have developed in the last lesson, in which I remind you we have seen what an asymptotic expansion is. And now it turns out, as we will see in a few minutes, that ray optics is actually an asymptotic approximation of the exact wave field representation, which would be a solution of the exact wave equations. Okay, to provide you a motivation for the ray optical approximation of the wave field, I will consider some basics about the electromagnetic field. And in particular, let us consider an electromagnetic field in free space, assuming that the free space is filled with a single non-conductive homogeneous medium, which is also isotropic, non-dispersive, so a very simple medium, which is described by its constitutive parameters epsilon, the permittivity, and mu, the permeability, magnetic permeability. Of course, since there is no conductance, the current J, the current density is equal to 0. And let us consider, inside this infinite space, entirely filled with this medium, which is homogeneous, a surface, let us call this surface sigma, where by assumption our time domain electromagnetic field has some sort of discontinuity. So we are interested in studying surfaces of discontinuity of the electromagnetic field. You, of course, know very well that when the medium is discontinuous, some components of the electromagnetic field are discontinuous across the interface between the two different media. However, the situation we are dealing with now is different because the medium is not discontinuous. There is only one medium, homogeneous in the entire space. However, it is possible that the electromagnetic field has some surface of discontinuity, and we are interested in characterizing the behavior of the field in a neighborhood of such surfaces. For instance, we may assume that the field is non-zero on one side of the surface. For example, on the negative side, here at the bottom, you can see the field E minus and H minus, which are equal respectively to E and H, some non-zero quantities. On the negative side of this surface sigma, which is orientable and has a unit normal n that points towards the positive side. Whereas on the positive side of the surface, you may assume that the electromagnetic field E plus and H plus is identically 0. Okay, this is our assumption. And let us try to develop some consequences from this assumption. In order to do that, we will consider the basic laws of the electromagnetic field. For example, we may consider the Gaussian law, which tells us that the magnetic field, or better, the magnetic induction B, has a zero flux across any closed surface. In particular, if you consider any volume, the flux of the magnetic induction B is 0 across the boundary of this volume. And in particular, we are, as usual, considering, in this case, an elementary volume, d omega, which is a parallelepiped whose sides ds and ds prime lie along the surface sigma. Since we are dealing with an infinitesimal volume, we can linearize our surface. So locally, we can represent it as if it were a plane. That's actually the tangent plane in the point P we are considering on this surface. And this parallelepiped also has a vertical dimension, dh, which is by assumption an infinitesimal of a higher order with respect to the other two. This is the small o notation, the Landau notation, which tells us exactly this, that we can neglect the thickness of this parallelepiped with respect to the other two linear dimensions. We establish also a local reference system with two unit vectors, tau and tau prime, in the plane tangent to our surface sigma, whereas n, the unit vector normal to the surface, completes this reference system, this frame, which is a right-handed frame, as you can see. Now, if we write this law, fundamental law, the zero flux of the magnetic induction for this elementary volume, well, it turns out that you can neglect the contribution of the lateral surface because of our assumption about dH, and so you remain only with the contribution of the upper and lower rectangles. The upper rectangle gives you a contribution which should be evaluated as an integral, but since the domain of integration is infinitesimal, we will approximate the integrand with the value it has, for example, at the center of the upper face, and write this value n dot b plus times the area of the upper face, which is the product of its linear dimensions, ds and ds prime. You do exactly the same on the lower face, where, however, the unit vector which points outwards with respect to the volume is now minus n, and in the lower face, of course, you have b minus. Okay, the area is exactly the same, so ds prime gets cancelled, and from this you get the elementary result that the normal component of the magnetic induction is continuous across the surface sigma. However, since by assumption on the positive side everything was zero, the electromagnetic field was identically zero, we end up drawing the conclusion that the normal component of the magnetic induction B must be zero also on the negative side. However, since the medium we are considering relates the induction and the magnetic field through a positive constant mu, this also implies that the normal component of the magnetic field H must be zero on the negative side. So the first physical conclusion we have is that on the surface of discontinuity sigma, the magnetic field must be purely tangential because it has no normal components on both sides. Okay. Of course, if we had considered the Gauss law for the electric induction, which is the dual of this law, we would get exactly the same conclusion. However, this time in terms of the electric field. So also for the electric field, we have that on the surface of discontinuity, the electric field must be purely tangential. Okay. And this is a first physical conclusion we have drawn from some basic law of electromagnetics, in particular the flux laws. However, we can say more if we consider the remaining basic laws of electromagnetics. For example, the Faraday-Neumann lens law, which relates the line integral of the electric field across a closed line, which is the boundary of a surface, and the time derivative with a changed sign of the magnetic induction across that surface. And the surface we will consider is again an infinitesimal one. For example, consider the surface ds, which belongs to the vertical plane which contains tau prime and n, as in this drawing here, and whose dimensions are ds prime and dh, which is again by assumption negligible with respect to ds prime. So the left-hand side is easy to see that since the vertical parts of this rectangle can be neglected, their contribution can be neglected with respect to the horizontal parts, then the contribution of the line integral at the left-hand side comes from the upper and lower segments, and therefore you get minus tau prime dot E plus times the length of the upper segment, ds prime, whereas on the lower side we have plus tau prime. As you can see, the direction is opposite on the two sides, dot E minus, and again the length of the lower segment, which is again ds prime. Now look at what happens. If the surface sigma were static, that is, it doesn't move in a space, then the right-hand side would simply be zero. Okay. And therefore, one would conclude that, as a consequence from this equation here, that the tangential electric field has no component along tau prime. because basically E plus is equal to 0, as we know by assumption. So its tau prime component is equal to 0. And this equation here would tell us, when you equate this to 0, that also the tau prime component of E minus must be 0. Now, of course, tau prime is an arbitrary vector in the tangent plane, so you would therefore conclude that the electric field has no tangential component at all. But since we know that the electric field is purely tangential from the previous slide, then we would come to the conclusion that the electric field E minus must be exactly 0, which contradicts our assumption, our initial assumption, that E minus here is instead different from 0. Okay? So therefore, we are forced to conclude that the surface sigma cannot be static, but the surface must move. And this is a first fundamental conclusion that comes directly from the basic Faraday-Neumann-Lenz law. If you have a surface of discontinuity of the electromagnetic field, that must move. So here we have the phenomenon of electromagnetic wave propagation built into the basic laws of electromagnetics. Let us see something more about this movement. Let us now assume that our surface is moving along the normal direction n with some velocity u. What changes in the previous reasoning? Okay, the left-hand side of our Faraday-Neumann-Lenz law remains the same. However, now the right-hand side is non-zero. Why is it non-zero? Well, basically because the flux of the magnetic induction now changes in time, so its derivative is non-zero. And why it changes? Well, it changes because the surface sigma is moving vertically along the n direction. So it sweeps this elementary surface ds, and therefore the flux across this surface changes. In particular, if you consider the infinitesimal time dt, during this infinitesimal time, our surface has moved of a quantity which is equal to the product of the velocity u and the time dt. So it sweeps this gray shaded area, okay, which gives you a contribution to the flux, an additional contribution to the flux. So the flux of the magnetic induction is increasing. And the increase in this flux is equal to tau dot b times the area of this shaded portion, which is ds prime, the horizontal dimension, times u dt, okay? But since we are considering the time derivative, this dt gets cancelled in the derivation, so you remain only with the velocity u. Or in terms of the magnetic field H, mu u tau dot h ds prime. The minus sign is, of course, built into the Faraday-Neumann's law. So, in the end, since E plus is equal to 0, by the initial assumption, we get that tau prime dot E times ds prime, so here, the left-hand side of the law, must be equal to minus mu u tau dot h ds prime. Now, it would be nice to have the same unit vector on the left and right-hand sides of this equation. However, on the left side, we have tau prime. On the right side, we have tau. So we do a little algebraic manipulation. We recall that tau prime is equal to n vector, the cross product of n and tau, because that was a right-handed reference frame. And we can also rewrite these in an equivalent way like this one. We exchange the position of tau and n by introducing a minus sign, and then we switch the dot and cross products, which is permissible, as you know. So in the end, we get that also on the left side, we have the tau unit vector. So we can write everything in the form tau dot n vector e is equal to mu u tau dot h. Now, again, tau was an arbitrary unit vector in the tangent plane, so this relation must be true for any choice of tau in the tangent plane, and so therefore you can get rid of tau dot and simply write this in the form n cross e is equal to mu u h. as is written here, n cross E is equal to mu UH. And dually, from the dual law of Maxwell, of Ampere-Maxwell, you would get exactly the same with the dual quantities. So n cross H is equal to minus epsilon U times the electric field E. Okay, this set of relations we have derived can be shown, and you should do that by exercise, to imply that the value of the velocity u must be equal to 1 over the square root of mu epsilon, which of course you will recognize is the velocity of light in the medium we are considering. It's not in vacuum. This is a typo. It would be in vacuums if the medium were the vacuum. Otherwise, it's the velocity of the light in the medium we are considering. But even more, so what have we discovered so far? We have discovered that if your electromagnetic field has a surface of discontinuity inside a homogeneous medium, this surface of discontinuity must move. So we have propagation. And how does the surface move? So it moves with the velocity of light along any normal direction. But even more, from this set of relations, another consequence is that the magnetic and the electric field are related, like in this equation, H is equal to 1 over zeta n cross E, where zeta is the characteristic impedance of the medium, the square root of the ratio between mu and epsilon. So the fields on the surface are purely tangential, as we have seen at the beginning, and they are related in exactly the same way as they are related in uniform plane waves, which are a very simple and basic solution of the Maxwell equations. Okay, so everything tells us that the surface of discontinuity, which we can now call a wavefront because there is propagation, is such that the field locally, so in the neighborhood of the points of this surface, behave as a uniform plane wave that propagates normally to the surface. So it's a TEM wave, a transverse electromagnetic wave, okay? Something very elementary and very well known. As time flows, of course, the surface of discontinuity, so the wavefront moves, and you can imagine to build an infinite set of such surfaces. There is one for each value of the function s, which we can introduce. So we can always write the equation, the Cartesian equation of the wavefronts, in this form by introducing some function s of the spatial coordinates, the position vector r, which is equated to time up to a constant, arbitrary constant factor, which has been chosen here as the velocity of light in vacuum. This time it's vacuum, exactly vacuum, so we call it c. Now, this function we have introduced to write down the Cartesian equation of the wavefronts is known as the Iconal function, which comes from the Greek word icon, which means the image, because it's the fundamental quantity to be studied in optical systems which form images. Here you can see a simple drawing in which you can see three surfaces in which the iconal is constant, which are the wavefronts at different times. And by definition, the lines orthogonal to those wavefronts are the rays. So here we introduce the concept of an optical ray. Now it's quite simple to derive an equation for the iconal. If you differentiate the equation of the wavefronts, you get that the differential of the iconal is equal to c, the velocity of light in vacuum, times the differential of time. However, if you move along the normal direction, then the differential of the position vector is parallel to the gradient of the iconal. And so you can also write that your differential ds is equal to the dot product, which is equal to the dot product of the gradient times the differential of the position vector. Then it's equal to the product of the absolute values of the gradient and of the differential of the position vector. The latter being equal, of course, to the product of the velocity u and the differential of time. So if you compare those two expressions, you find that the absolute value of the gradient of the iconal is equal to the ratio between the velocity of light in vacuum and the velocity of light u in the medium, which by definition is the refractive index of the medium. So the square root of the product of the relative constitutive parameters. And so if you square now, in order to get rid of the square root which is built inside the absolute value, then you obtain what is known as the Iconal equation, which is a partial differential equation whose unknown is the Iconal function S, whereas the right-hand side is by assumption known. So it's the distribution of the refractive index in your medium, which can now be thought as a non-homogeneous medium, because this approach can be generalized to non-homogeneous media. Now, the Iconal equation, as you can see, is a nonlinear first-order partial differential equation. It's nonlinear because here you have the square of the absolute value of the gradient, so you get the powers of the spatial derivatives. If you, in particular, introduce a new function, capital Phi, as the Iconal minus Ct, then it's easy to see that the Iconal equation implies that it's true that the squared absolute value of the gradient of this new function Phi minus n squared over c squared times the squared time derivative of the new function Phi, well, this must be equal to 0. Now, this kind of equation reminds us of the wave equation, which is a different equation, because instead of having the square of the absolute value of the gradient, we have instead the Laplacian, which is a second-order differential operator, and instead of having the square of the first derivative, we have the second derivative. So the wave equation is linear, but is second-order. However, in the study of partial differential equations, it is known that if you take a second-order equation, like the wave equation, and if you replace any higher-order derivative with the corresponding power of the first-order derivative, then what you get is an associated nonlinear equation, which is known as the characteristic equation. And in this case, we have discovered in particular that our function Phi, capital Phi, satisfies the characteristic equation of the wave equation. Why is this important? Because in mathematics, you can show that any discontinuity in the solution of the wave equation in particular must be constant on the surfaces, must occur exactly on the surfaces where the solutions of the characteristic equation related to the wave equation are constant. So we have found that the wavefronts, that is the surfaces where the Iconal is constant, they are the surfaces where our wave equation has discontinuities, which was by our initial assumption about the electromagnetic field. So all these has been said with the goal of providing you some physical motivation for the so-called Ansatz, which is a German word which means the initial assumption on the basis of a theory. The Ansatz of the ray optics is that locally your electromagnetic field behaves like a uniform plane wave, which is what we have discovered to be true in the neighborhood of the wavefronts. Now, since the wavefront is a place where the electromagnetic field has a discontinuity, then you can imagine that for the properties of the Fourier transform, a discontinuity gives rise to the part of the spectrum which is located at high frequencies, high temporal frequencies. So if we are looking for an approximation of the exact electromagnetic field, which is valid in the asymptotic limit in which the frequency is high, so in the limit of infinite frequency, let's say, or very high frequency, then this corresponds to the behavior of the electromagnetic field close to the surfaces of discontinuity. And we have discovered that this behavior is exactly the behavior of a uniform plane wave. So the ansatz of the ray optics theory is that, for example, the electric field can be written in this form, which reminds us of a uniform plane wave. We have a vector E0, which is generally a function of the position r, times an exponential, which reminds us of the propagation exponential of uniform plane waves, in which, however, in the exponent, instead of having the usual dot product between the propagation vector k and the position vector r, you have the Iconal function times the k0 constant, which is the free space wave number. This generalizes the uniform plane wave because first, the E0 vector is not constant, but it's a function of position, and also the phase, so the argument of this term, the exponential term, is not linear in the position vector, but may be generally nonlinear and expressed by an Iconal function, a general Iconal function. Of course, we are assuming that these functions E0 and S, the Iconal, are slowly varying functions. That is, they vary along characteristic lengths which are large with respect to the scale of variation of the phase of our electromagnetic field, and the latter is, of course, the wavelength. So we are assuming that our electromagnetic field looks like a plane wave locally. The characteristics of this plane wave, however, vary from point to point, but they do so in a slow manner with respect to the wavelength, which is our reference scale to compare with. Of course, these functions E0 and S are assumed to be independent of frequencies contained inside the wave number K0. So the only dependence on frequency is because of the presence of this K0 factor. Okay? If you insert this form of the electric field and also of the magnetic field inside Maxwell equations, and this is something very instructive to do by hand, you will discover that Maxwell equations, in particular the curl equations, are the first two, and the divergence equations are the latter two in this set of four relations, can be written as is shown in this slide, where the terms have been arranged so to show explicitly the presence of the K0 factor, which you can imagine is a factor that tends to infinity when the frequency is very large. This is important to notice, because in this limit, the terms containing the factor 1 over K0 can be neglected. And then if you neglect them and you left multiply everything by the gradient of the Iconal, then, again, you can do some algebra by exercise. You will discover that the gradient of the Iconal cross the gradient again of the Iconal cross the electric field E0 minus n squared E0, which is something that can be rewritten as you can see here because of the properties of the double cross vector product. Well, these, because of the Iconal because of the algebraic relations, can be written also in this way: n squared minus the square absolute value of the gradient of S times E0. This must be equal to the zero vector. Of course, if you have a non-trivial solution for the electric field, the term E0 must be different from zero, and you must come to the conclusion that the term in square brackets must be zero, which is equivalent to saying that the Iconal equation holds. So again, we reobtain the Iconal equation directly from Maxwell equations. The problem with this very simple approach is that for finite frequencies, so any concrete frequency which is maybe high but not infinite, we are not able to appreciate in advance the error we are committing by approximating the electromagnetic field in this way. So in order to be able to appreciate the accuracy of this representation, what we need is a full asymptotic expansion. So not only the first term, which is the ray optical term, but also all the other terms. In order to show you how to obtain this full asymptotic expansion, I will start with the simpler case of a scalar wave field, which is something much used in optics, because even though the electromagnetic field is, of course, vectorial, in the high frequency limit, and if you are considering in particular free space propagation, usually it's quite accurate, even though it's not exact, to consider only one generic scalar component of the field or of the potential and call this a disturbance. We will call it U generically. And to consider that this quantity satisfies a sort of generalized Helmholtz equation, like this, in which you have the Laplacian of U, and a second addend in which you have K0 squared times the square of the refractive index. This is correct for media whose refraction index varies on a slow scale, a slow spatial scale with respect to wavelength. So our starting point is Helmholtz equation for our scalar quantity U. And sì, certo. Ok, thanks. And what we are aiming now is to find an asymptotic representation of the solution of this scalar Helmholtz equation in the limit valid in the limit of high frequency, that is, in the limit of large K0. So just let me one moment switch to Google Meet just to see if there is any question because of our problems with the earphones. Okay, I can go on. This asymptotic series can be written in this way very naturally. We have the propagation factor of the uniform plane wave, the exponential, in which the iconal is in the exponent. And then you have the infinite summation, in which you have inverse powers of the frequency, in particular of this factor minus jk0, with coefficients a sub m. The index m goes from 0 to infinity. Of course, the 0 index corresponds to the ray optical solution. And this must be understood in an asymptotic sense, as we now know, because of this tilde. So it's not an exact equality, but this holds asymptotically, exactly in the technical meaning we discussed in the last lesson. This is known as the asymptotic series of Luneburg and Klein, by the name of two scientists who introduced this in the 40s of the last century. Okay, if you introduce this series inside the Helmholtz equation and you perform some algebra, you will discover that the following must be true. That is, the sum for the index m, which goes from 0 to capital N, of qm over minus jk0 to m minus 2 must be a quantity much smaller than k0 up to minus n, where the numerators qm are defined as here in the center of this slide. In particular, q0 is the difference between the square absolute value of the gradient of the diagonal minus n squared. Then there is q1 and other, etc. Now, this may hold, this equality on the top may hold for any index n, capital N, only if all those numerators are identically 0. And this in turn yields a set of equations which involve both the iconal S and all the coefficients in the asymptotic development A sub m. If you look at the lowest order relation, that the one that involves Q0, for example, well, you can see that in this relation you have only the iconal, so no other quantities involved. And in particular, if you equate to 0 Q0, you again obtain the Iconal equation. Okay, so this is a third way of deriving the Iconal equation. And now this Iconal equation has some consequences. For example, if you consider to have a single valued Iconal S, because in general it is possible that the Iconal has also multiple values, which simply says that in your region of space you don't have only a bundle of rays, but you have many bundles of rays, maybe because of some reflection somewhere. So at a given point you don't have only one ray, but more than one ray. But to keep things simple, let us consider a single bundle of rays, so a single value diagonal. If we define the unit vector here, S with a hat, as by definition the gradient of the iconal divided by its absolute value, since the Iconal equation tells us that the absolute value is equal to the refractive index, we can also replace the denominator here with the refractive index of the medium, n. And let us now study the rays, that is the trajectories, the lines whose tangent is equal to this unit vector S hat at each point in space. Now, if S is the curvilinear abscissa along our ray, then we can write that the product of n times the derivative of the position vector with respect to the curvilinear abscissa, which is by definition the unit vector S hat, well, this must be equal, from the relation you can see here on the top, to the gradient of the iconal. Well, this is some sort of local wave vector. So k, the vector k divided by k0, this is a local wave vector of our local representation of the quantity u in terms of a local plane wave. Here you can see the rays, which come orthogonal to our wavefront at each point with the unit vector s in black. Now, with some algebra, we can also obtain a differential equation for the rays. In particular, if you differentiate what we have obtained with respect to the abscissa S, which is equivalent to projecting the gradient onto the unit vector S hat, then you will write that S hat dot the gradient of n times the derivative dr over ds, we are here. And this again can be rewritten considering that the quantity in brackets, as we have seen, must be equal to the gradient of the iconal. And again, the unit vector S is by definition the gradient of S divided by the refractive index. So we have reached this stage where you have 1 over the refractive index, the gradient of the iconal, dot the diagonal gradient of the iconal, which is of course a tensor of order 2 or a dyadic. Now, this expression, the product of the gradient dot a double gradient, comes about when you try to develop this expression here, the gradient of a dot product, because from elementary differential algebra, this development involves the double product of the gradient times the curl of the gradient of S, which is of course 0 because the curl of any gradient is identically 0. And here you have the double product of the dot product of the gradient S and the double gradient. So everything can be rewritten as 1 over the refractive index times 1 over 2 times the gradient of the dot product of the gradient of the iconal, which, however, by the Iconal equation again, is equal to n squared. So you can collapse this into this right-hand side here, where now the gradient of n squared is, of course, equal to twice the gradient of n. So the factor 2 in the denominator gets cancelled, and you have also the factor n, which comes from the derivative, which cancels the denominator here, n, and finally, you simply have the gradient of the refractive index. So if you join the left-hand side, the extreme left-hand side, and the extreme right-hand side, what you get is a differential equation whose unknown is the position vector as a function of the curvilinear abscissa S. This is an ordinary differential equation, not a partial differential equation, which is known as the ray equation. It's a second-order ordinary differential equation, which is generally nonlinear because if you have a non-homogeneous medium, then you have this n function of the coordinates which enters inside this left-hand side. However, in a homogeneous medium, the equation becomes very simple. It becomes linear because it tells us that the second derivative of r must be equal to 0, which means that the vector r, which is now, this should be written as a vector, so in bold, that must be a linear function of the curvilinear abscissa. So you can see that this position vector must be equal to a constant r sub 0 plus a linear function of S, which can be written, of course, as S times this unit vector S hat. So basically, we have that the rays in a uniform medium must be straight lines. So light propagates straight in a uniform medium, which is something very well known, okay? Whereas in a medium which is not homogeneous, light, or better, the high-frequency field we are considering does not propagate in straight. And in particular, if we remember some elementary differential geometry, in particular the so-called Fermat equations, which give us information about the derivatives of the unit vectors associated to a curve with respect to the curvilinear abscissa, where the unit vectors are S hat, which is the unit vector tangent to our ray, as you can see in this picture. Then there is the unit vector n, which is orthogonal to the plane which locally contains the ray. This is known as the osculating plane. And this unit vector n points towards the center of this circle, the osculating circle, which is the best circle, the circle that best approximates our ray locally. And finally, you complete your reference frame with the unit vector b, which is orthogonal to both S and n, okay? you will find in differential geometry that the derivatives of those unit vectors with respect to the abscissa S can be written in terms of the unit vectors themselves by introducing some coefficients which depend on the so-called curvature radius, rho, here. And here you have another coefficient which is known as the torsion, which tells you how much your curve is not plane. So it goes outside the locally osculating plane. Okay, from those equations, we have from the ray equation that the gradient of n, the refractive index, which is equal to the derivative of the product n times s hat. By those equations, those Frenet equations, you can write this derivative as the sum of two terms. One is proportional to s hat, and the other one is proportional to n hat. And this tells us, first, that the ray lies locally in the plane formed by the gradient of n and s. Second, if you project this gradient onto the unit vector n, you will discover that this projection, which is the ratio between the refractive index and the radius of curvature, is a positive quantity. This means that your ray bends towards the gradient of n. So the rays tends to go where the refractive index is higher, okay? Which is something very familiar, because if you have an interface between a medium with a lower refractive index and a higher refractive index, and you have a ray that comes onto the interface from the lower medium, then you know by the Snell law that this ray gets bent and it becomes closer to the normal, to the interface, if you go from the lowest to the higher, from the lower to the higher refractive index. So rays tends to go towards the higher indices. So this is the more or less the kind of qualitative information we can get from the ray equation. We can also add this theorem that is known as the Malus-Dupin Theorem. The ray equation gives us a differential equation that expresses a necessary condition for a ray bundle to be orthogonal to a family of given wavefronts, but it is not sufficient to imply the existence of the iconal. So if you go from the iconal to the rays, everything is okay, because once you are given the iconal, you get in a unique way the rays. But if you are given the rays, so a family of lines in space, and you ask yourself if there is an iconal really associated with those rays, well, this is not always true. For the iconal to exist, you must also enforce this additional condition, that is, the curl of the product n times s hat must be equal to 0. And it can be shown that if this condition in the box holds at one point, then it holds everywhere. So it's enough to hold at one point, also in the presence of discontinuities of the refractive index. So if you have, for example, a ray bundle associated to an iconal which enters an optical instrument, the Malus-Dupin theorem guarantees that on the exit side of the optical instrument, you still have a ray bundle which can be associated to an iconal. So you can describe the field in any point of your system in terms of some iconal, which is of course convenient. Okay, let us make a short detour about the rays, in saying something about their variational properties, because they are very useful in practice and important also in theory. Let us define the so-called optical path along a general curve gamma, not necessarily along a ray. So we are given an arbitrary arc gamma which joins the points A and B in space, which is parameterized by some parameter t, which is not necessarily time. And let us define the optical path as the integral along gamma of the product of the refractive index n and the elementary length ds. So in terms of the parameter t, you have an integral from ta to tb, which are the limits of integration corresponding to the endpoints, of the product of the refractive index n and the absolute value of the derivative r prime as a function of t. Okay, this must be integrated with respect to t. So we have here a functional. There is some law that gives you a number if you are given the equation of your arc. So if you are given the function r of t, this is a recipe for calculating the optical path that is a functional. In abstract terms, it can be written in this way, as in the box here. It's an integral with respect to some scalar quantity x of an integrand which depends on x, of course, but also on y and y prime, where y is a function of the parameter x. Of course, in our example above, x is the parameter t, y as a function of x is r as a function of t, and a and b corresponds to the integration limits. We are interested in characterizing the conditions under which this functional is extremal. So it's we wish to find the point of stationarity of this functional, minima, maxima, inflection points. Okay. If this were a function of a single real variable, we could talk about minima, maxima, inflection points. Here we are generalizing those concepts to the case of a functional. And in order to do that, we will make a variation of the function y. For example, we can imagine that our function y is the sum of a given function f plus some multiple of another function g characterized by being equal to 0 at the extremes. So once you do this linear combination, you obtain a variation of your function y, which however still remains always the same at the extremes. Okay, so imagine that you are varying your path, however you maintain the endpoints fixed. If you do that, you will discover that your functional becomes a function of this free parameter alpha, because now y becomes a function of alpha inside the integral. If you differentiate now your functional as a function of the parameter alpha, this is an ordinary derivative. You can do that by differentiating under the integral sign, and you discover that your integrand becomes the sum of two addends. In the first one, you have calculated the gradient of the function f with respect to its argument y. In the second addend, you have calculated the gradient with respect to the other argument, y prime. And in particular, the latter addend can be manipulated by integrating by parts in order to shift the derivation from the function f, from the function g, sorry, to the gradient. If you do that, you will be able to factor out the quantity g, which was, by the way, arbitrary. And you will discover that if you enforce the condition of stationarity, that is, this derivative in the left-hand side must be equal to 0 to have stationary points. And if you want that this is true for any choice of your function g, then you must conclude that the quantity in brackets inside the integral must be equal to 0. Now, this quantity in brackets gives you actually a differential equation, which is a necessary condition if you want to have a stationary point of your functional, and this is technically known as the Euler-Lagrange system of differential equations associated with your functional. If you have studied analytical mechanics, of course, you know very well what I'm speaking about. This is exactly. In this case, the functional is the optical path. No, it has to do very much, because there is a perfect... Oh, no. Okay. It's not a Lagrangian initial, it's the optical path. It's just a definition. However, there is a one-to-one correspondence between the mechanical concepts and the optical concepts, as we will see in a moment, because if we specialize everything now to the case of the optical path, so the integrand now is the product of the refractive index and the absolute value of r prime, and if you perform with patience all the steps, so you calculate the gradients, which turn out to be characterized by these expressions here, then the Euler-Lagrange equations can be written in this way, and you will discover, of course, as expected, the ray equation. That is, the Euler-Lagrange equation, which express the stationarity of the optical path, turn out to be the ray equations. So the rays are exactly those paths along which the optical path is stationary, and this is, of course, the principle which was stated by Fermat in the 17th century in rather theological terms, that is, the light goes along the shortest paths. this is useful in addition to be interesting because there is a close relationship between what happens in electromagnetics and in optics, which is an asymptotic approximation, and, for example, what happens in analytical mechanics, or even better if you consider the transition, the classical approximation of quantum mechanics to ordinary Newtonian mechanics, then the mathematics is exactly the same, okay? But it has also practical applications, because once you have discovered that rays satisfy this variational principle of Fermat, then you can draw some conclusion about, for example, reflectors. Because, for example, if you have a parabolic reflector, because of the metric properties of this curve, which tells you that the distance of a general point on the parabola is equal if you calculate it from the focus or from the directrix, then it turns out that if you have rays coming out of the focus, then those rays are bent by reflection upon the parabolic mirror, exactly all in the same direction, which is the direction of the axis of symmetry of the parabola. And this is, of course, the principle of operation of any parabolic reflector. But also, you can consider ellipses or hyperbolas whose equations are characterized by the metric properties of stationarity of the sum of paths, for example, coming out of the foci in the case of the ellipse, or the difference in the case of the hyperbola. And as a consequence, you have all those antenna reflector configurations which are based on the conical sections. For example, here you can see a big Cassegrain configuration in which you have a parabolic big reflector, which is fed indirectly. Here is the feeder, but the feeder actually illuminates a hyperbolic subreflector. So everything works because of this principle of Fermat, which tells us that the rays follow a stationary path. Okay, so if you are placing the feeder in the focus, in one of the two foci of the hyperbola, and the hyperbola is the other as this focus coincident with the focus of the parabola, then everything works, and in the end your rays will come up straight and parallel out of this antenna system. Okay. Okay, I think that it's 11 o'clock, so let's make some break. So see you in 10 minutes or so. Scusi Roberto, ma ho visto soltanto adesso che lei mi chiedeva di partecipare, ma purtroppo ho dei problemi con l'audio e non sento. E non so da quanto tempo mi stesse chiedendo di partecipare, l'ho visto solo adesso. Adesso sto facendo un break di 10 minuti, riprendiamo tra poco. Okay, I hope you can hear me again. We are about to start the second part of this lesson. Okay, so we have seen so far the consequences of the first of these infinite set of relations, the first one which involves the Q0 coefficient, which tells us that the Iconal equation must be satisfied. Now we turn our attention to the next relation, which tells us that the Q1 coefficient must be equal to 0, and this is known as the field transport equation for the coefficient A0. This equation involves, in fact, A0 and also the Iconal S. So the idea is, first we solve the Iconal equation, then we know the Iconal function S, and we use this into this field transport equation, which is now to be seen as an equation in the unknown A0. A0 is the first of those infinite set of coefficients which are the numerators in the Luneburg-Kline expansion. Once we have done this, we can go to the next relation, the one that involves Q2, and go in this way up to any desired order. As you can see, the mth of those relations involves the Iconal, always, and two of those coefficients, a m-1 and a m-2. So you can solve this infinite set of equations recursively, basically. We will do that explicitly for A0, in particular from the field transport equation, which can be written, as you can see here at the left bottom, A0 times the Laplacian of S, plus twice the dot product of the gradient of S times the gradient of A0. This must be equal to 0. Well, this can be written multiplying everything by A0, as you can see here. And now the Laplacian, as you know, is the dot product of the gradient, it's the divergence, that is the dot product of the del operator and the gradient. Now the gradient of S is, and by the Iconal equation, equal to the refractive index times the unit vector S hat. This is also exploited in the second addend. And in the second addend, you also have twice the product of A0 times its gradient, which is by definition the gradient of A0 squared. So everything can be compacted, exploiting another elementary differential identity, as the divergence of the quantity inside these brackets here, which is A0 squared times the refractive index times S hat. This divergence must be equal to 0, and this is what tells us the field transport equation for A0. Now, if you have a solenoidal vector, that is a vector whose divergence is equal to 0, this means that if you consider the lines of force of this solenoidal vector, you have conservation of flux. If you consider a tube, a bundle of lines of force of this vector, then basically you have the conservation of flux. So it's in a hydrodynamic analogy with the movement of a fluid, but also you can think of the Poynting vector associated to an electromagnetic field, whose lines of force give you the flow of power, which is conserved along any tube. So, for example, if you consider that your wave field is being approximated at the lowest order like a plane wave, so this is the ray optical approximation, then the field transport equation of order 0 tells us that the quantity A0 squared n S hat behaves like the Poynting vector, that is, its flux across any surface orthogonal to the lines must remain equal. So if you can see easily that if your tube of flux shrinks, so the area gets reduced, like in this picture, then this of course means that the amplitude A0 must be increased proportionally to the square root of the areas. So you have a law of variation of the amplitude along a ray. So if you are given the amplitude at a certain reference position S0, and this is this term here, then at another position along the same ray, say the position corresponding to the abscissa S, the amplitude will be related to the amplitude, the initial amplitude, times the ratio of the areas up to 1/2. So the square root of the ratio of the areas multiplied by the refractive index because of the presence of the refractive index inside here. Okay. Now we will write again the transport equation in a still different matter. Again, the gradient of the Iconal is equal to n times s hat, and in this way you will see that this second addend here can be written as the product of the refractive index times the derivative along s with respect to s of a0. If you divide the transport equation by a0, the first addend remains with the Laplacian alone, and the second addend now contains 1/a0 times the derivative of a0, so the derivative of the logarithm of a0 with respect to s. And then there is the coefficient twice the refractive index. Now this is a first order differential equation in a0, which can be solved immediately. Once you know the initial amplitude a0 in a reference position S0, then you get the amplitude at any other position S by multiplying the initial amplitude times the exponential you can see here, which is an exponential whose exponent is the integral with a sign, minus sign in front of it, from S0 to S of the ratio between the Laplacian on the Iconal and the refractive index. Now, we have seen that if the tube shrinks, then the amplitude must increase. So if the area of the cross section goes to 0, the amplitude must go to infinity. And this in turn implies, given this explicit representation of the amplitude, that in this limit the Laplacian of the Iconal must go to minus infinity if we want this exponential to go to plus infinity. So every time we have a shrinkage of a bundle of rays, for example, if you have a focus of a lens, then ray optics tells us that the amplitude should go to infinity, which is of course non-physical, but this simply means that in a neighborhood of the focus, ray optics cannot hold anymore. And it does not hold anymore because the Laplacian going to infinity means that the Iconal varies very rapidly in space, which is against our assumption that everything varies very smoothly on the scale of the wavelength. But it's interesting to see what happens at those points where ray optics fails. And those points, for example, are the points which belong to the so-called caustics, which by definition are the envelopes of the ray bundles. So here you can see in red the trace of a caustic. You can see two rays which are tangent to the caustic, and those two rays intersect at a given point in a neighborhood of the caustic. Since you have two rays, you have two wave fields which superimpose at the point P. So what you get is interference, and so an oscillatory behavior of the wave field in the neighborhood of the caustic as concerns the phase. But it's easy to see that as concerns the amplitude must go to infinity if you approach the caustic. For example, if you consider a zoomed version of what happens here in this elementary triangle shaded in gray, in which you have one curved side belongs to the caustic, then there is a straight side belonging to the ray R2, and then there is a curved side belonging to the wavefront where the Iconal is constant and is equal to S2. Okay, if you calculate the Laplacian of the Iconal as the divergence of the gradient, since the gradient is the product of n times the unit vector s, you will see that the unit vector is, by definition, parallel to the ray. So it's directed along the ray on this side, but it's also tangent to the caustic, which is an envelope of rays. So the only side of this triangle which gives you a non-zero contribution to the flux of the quantity ns hat is this yellow side. Why are we interested in the flux? Well, because, as you know, the divergence is locally the ratio between the flux of the vector and the area of the domain on which you calculate the flux. Okay, so the area of this gray triangle. Now, the area of this gray triangle is of the order of the product of the length of the two sides, delta and capital delta. okay? Whereas this flux gets contribution, as I said, only from the yellow side, and therefore, as you can see immediately, this contribution is equal to the refractive index n times the length of that side. So you have that capital delta gets cancelled, and in the end, this Laplacian of the Iconal is a function that goes as 1 over small delta, which is the distance between the point P and the point where the ray touches the caustic. So if you now let delta, small delta, go to 0 because the point P along the ray approaches the caustic, you discover that this Laplacian goes to minus infinity. And this tells us, as we saw in the previous slide, that the amplitude must go to infinity, so it must explode. So there is a very high value locally of the field, which is of course physically not infinite, but it's a very high value. So caustics can easily be seen because they shine to our eyes. And here is an example. You can also have a more complicated situation when your caustic is not a regular curve, but it may have some discontinuity in the derivative, like a cusp. This is very common if you let some light shine on the bottom of a cup. You get this nice picture, which is an aneroid curve, which is very easy to obtain. And this is the trace of our caustic with a cusp. And now the behavior of the field close to a cusp is even more complicated because you have interference of not 2 but 3 rays in a neighborhood. So you have still different behavior of the amplitude, which anyway goes to infinity in the neighborhood of the cusp. Okay. Now, in the particularly simple case of a homogeneous medium, it turns out that the caustics are the loci of the principal centers of curvature of the wavefront. So if you consider a point O on the wavefront and you define the principal sections as those sections where the curvature has their minima and maxima, its minima and maxima, then the radius of curvature will be 2 points, O1 and O2. If you let the point O vary along your wavefront, those points O1 and O2 will also vary, and they will describe a two-sheeted surface, which is, by definition, the caustic of your wavefront. Now, it turns out, without entering into the details, that the Laplacian of the Iconal can be, which is by definition the trace of the double gradient, can be written in terms of the radii of curvature, rho 1 and rho 2 associated with those two centers of curvature. And so, if you are on the curvature, this means that at least one of those radii must go to 0. Here you have an example. If you consider the ray optical approximation to a cylindrical wave, which is a wave that does not depend on the axial direction z, and to keep things simple, we will also assume that it does not depend on the azimuthal angle phi, so it's an omnidirectional cylindrical wave. Then you can try to find a solution, an approximate asymptotic solution to the Helmholtz equation by looking for a solution in the form of this Luneburg-Kline series, where now the Iconal equation tells us, since the Iconal depends only on the radial coordinate rho, that the absolute value of the derivative of the Iconal with respect to rho, that must be equal to the refractive index. If the index is a constant, like in a homogeneous medium, then you can solve immediately this equation and you will find that your Iconal is a linear function of rho. Okay, so the surfaces where the Iconal is constant are those cylinders where rho is constant. So those are the wavefronts. And the rays are the associated straight lines that originate from the z-axis and go to infinity radially outwards. Okay, in this particular example, this is an outgoing wave, of course, so we are assuming that some source is located along the z-axis that produces this wave, and the wave propagates all the way to infinity in the outward direction. Okay, in this situation, the caustics are made from, they collapse into the z-axis on one side, and the other sheet of the caustics goes to a circle at infinity. Once you have the Iconal, you can go to the transport equation and calculate the amplitude. Now, without going into the derivation, which is very simple, because now we know the Iconal, so we can do all the calculations analytically, it turns out that the amplitude along a ray has a dependence on the radial coordinate rho as the inverse of rho to 1/2, which is exactly what we would expect from a cylindrical wave because of conservation of power. The amplitude must decay by increasing rho, and it must do so in order to maintain the power flux the same across any wavefront. So this is the 1/2 exponent here, which gives you this conservation of power. Therefore, we have characterized the lowest asymptotic order because now we know the Iconal and the coefficient A0. The lowest asymptotic order is of the kind an exponential e to minus j n k0 rho, the propagation factor, divided by rho to 1/2. And you can compare this with what we know is the exact solution of the Helmholtz equation, because we are able to solve exactly the Helmholtz equation in cylindrical coordinates. The solution is the Hankel function of order 0 and of the second kind if we are assuming an outgoing wave with an exponential j omega t dependence on time. Now, this Hankel function has many properties, among which we know its asymptotic development for high values of its argument. So when the argument becomes a very large number in absolute value, the Hankel function can be approximated as the product of this square root, where you have rho inside the denominator of the fraction, and then there is the exponential that gives you the radial propagation. So it's exactly of the kind we have found by solving the Iconal and transport equation to the lowest order. Okay. Just to give you an example, another example would be a spherical wave. And again, we will look for a solution which does not depend on angles. So it's an omnidirectional spherical wave. In this case, the Iconal equation tells us that the derivative, the radial derivative of the Iconal is a constant in a homogeneous medium. And so therefore the Iconal, which is a function of r and not of rho, this is typo, must be a linear function of the radial distance. So again, the wavefronts are spheres. Now the source is assumed to be located at the origin. This produces spherical wavefronts that express the propagation of the wave to infinity in the radial direction. The rays are now a family of lines, straight lines, that originate all from the origin, and the origin is the caustic. Our caustic surface collapses to the origin in this particular example. It's the center of curvature of all the points on those spherical wavefronts. Again, once you have the Iconal, you can calculate the amplitude at the lowest order from the transport equation. And in this case, as you would expect, the amplitude is inversely proportional to the radial distance, because now we are spreading in 3 dimensions. So the amplitude must go as 1/r. And so to the lowest order, we have this kind of behavior. The radial propagation factor in the exponential in the numerator, and the spreading factor in the denominator, which guarantees that power is conserved across any wavefront. Now, in this particular case, it turns out that the lowest order is also exact, because we know that the exact solution of the wave equation is nothing different but the 3-dimensional free space Green's function, which is the exponential divided by 4 pi r. And this is exactly what we have obtained from the ray optics approximation, which is in this case not an approximation, but it's exact. They vanish. It is possible to generalize all these to the case of a complex Iconal. This has been done by Felsen in the 70s. So you have a real part, but also an imaginary part, I. So you have not only phase fronts, but also phase paths where the amplitude is constant. And why is it useful to do this generalization? Well, because it's In this way, you are generalizing your assumption that the wave can be locally represented as a uniform plane wave. In this case, you are representing your wave field in terms of a plane wave which is not necessarily uniform. It can also be an evanescent plane wave, and this is useful in a number of situations. For example, if you have the field exterior to a plane dielectric layer, it is possible, if you consider, for example, the propagation of a surface wave guided by the dielectric layer, what happens is that the field is actually evanescent outside the dielectric, the guiding region. But also you can have a weakly evanescent field outside the curved dielectric layer for the same reason, and in this case you would also get some kind of radiation. But this also happens in free space when you have a Gaussian beam that you may know is a solution of the paraxial wave equation, and which is also characterized by a locally evanescent behavior. So this has been done. We will not go into the details. What I will tell you in what remains of this lesson is what happens when you restore the vectorial character of the field. If you may remember that at the beginning I considered the scalar approximation of the electromagnetic field, which is very common in optics. However, if you wish, you can also use the full vectorial representation of the electromagnetic field. This is, of course, mandatory if you wish to study properties related to, for instance, the polarization of the field, which is intrinsically something that must be described in vector terms. Now, if you consider a generally inhomogeneous medium, for example, a dielectric medium, from Maxwell equation, you can derive this sort of generalized Helmholtz equation in which you have the familiar two first addends, and then you have this additional term, which is zero if the medium is homogeneous, because you can see here you have the gradient of the logarithm of the refractive index. So if the refractive index is a constant, this gradient is equal to zero. And we look for a ray optical approximation to the solution. So again, the full original Luneburg-Kline asymptotic series. However, now this is in vector form, so the numerators are vector functions of the position vector r. Okay, without doing all the calculations that I'm sure you will do by yourself, you will discover again that to lowest order you will find the Iconal equation. And then going to higher orders, you will discover an infinite set of transport equations. The first one involves only the amplitude vector E0, okay? And the remaining infinite ones involve both EM and EM minus 1, where M is a positive integer index, okay? If you compare these equations with those obtained in the scalar approximation, we can see that in some lucky situation, the vector theory collapses into the scalar theory. For example, this happens when all the coefficients E sub m are perpendicular to the gradient of the refractive index. So, for example, if you have a medium whose refractive index varies only in a given plane, and your electric field is perpendicular to that plane, then in that case you can still use the scalar approximation. However, in general, this will not happen, so all the scalar components of the electric field get mixed because of the term containing the gradient of the logarithm of the refractive index. So even if you start, for example, with a field which is initially linearly polarized, this linear polarization will not be maintained during the propagation. So along a ray, polarization will not in general be maintained. It is possible to study exactly what happens along a given ray if you introduce a vector E prime, which is related to the lowest order vector E0 in this way, through this exponential, which is the same exponential we encountered in the field transport equation solution. Then it is easy to see that the lowest order of those transport equations can be rewritten in a nice compact way, like this. And now, if you multiply this scalarly by S hat and you make use again of the ray equation, you will discover, without doing the steps one by one, I will only discuss the final result, which is the blue one here. You will discover that the derivative with respect to the abscissa S of this quantity in brackets must be equal to 0. So this tells us that the quantity in brackets is a constant along the ray, which is something useful because now we have information about the behavior of E0 along the ray. In particular, for example, if E prime is perpendicular to the ray at one point, it will remain perpendicular forever, because in that case, this dot product here is equal to 0, and if this must be a constant, it will remain 0 along any point in the ray, along the ray. If you further multiply the transport equation by E prime, you will instead discover another interesting fact, that is that the derivative of the dot product of E prime with itself is equal to 0, which means that that dot product must also be a constant along the ray. So E prime is a constant amplitude vector along the ray, and if it is orthogonal to the ray at one point, it will also remain orthogonal along the ray. Those two informations give you a way to characterize the variational polarization along a given ray or an arbitrary ray. Finally, once you have found everything about your electric field, you take the first of Maxwell equations, with the curl, and you will calculate the magnetic field, which is its counterpart, discovering that, as you would expect, also the magnetic field can be represented in exactly the same way as the electric field, that is, in terms of an asymptotic series, which has the same form as the one we have used for the electric field, where now, of course, the coefficients in the numerator are different. They are called HM. However, those coefficients can be calculated in terms of the EM coefficients for the electric field. In particular, the lowest order relation between H0 and E0 is interesting because you can recognize again the relation between the electric and magnetic field, which holds for a uniform plane wave. So again, we will find that to lowest order, that is in the ray optical approximation, which is the lowest order of this asymptotic series, the field behaves locally exactly like a uniform plane wave, which is a transverse electromagnetic wave with respect to the local direction of propagation, which is orthogonal to the wavefront. And the relation involves, of course, the parameter zeta, which is the characteristic impedance of the medium. To finish, ray optics is, of course, an approximate theory. It is an asymptotic theory which loses validity in some regions of space, as I have already mentioned. For example, along the acoustic, or even worse, in the neighborhood of a focus, because of the divergence that it predicts, which is non-physical. So in a neighborhood of those points, ray optics cannot be an accurate representation of the wave field. But also, for example, in scattering problems, if you illuminate an object with a bundle of rays, you cannot expect the theory to be accurate, for example, on the shadow boundary, which is the boundaries between the lit and the dark regions beyond the object, because any discontinuity in the field is non-physical. Any solution of the field in a homogeneous region must be, this can be shown rigorously, must be analytic, so it's a continuous function of space, whereas ray optics would by itself predict the discontinuity between shadow and light. Okay. Something similar occurs also when you have grazing incidence on curved surfaces, but also when you are impinging on some sharp wedges or tips, that is, places where your surfaces exhibit an infinite local curvature radius. Okay. In those cases, like in the case where you are impinging on a planar interface, different phenomena may occur, which are generally called diffraction phenomena. By definition, diffraction, as Arnold Sommerfeld defined it, is everything which goes beyond ray optics. So when ray optic fails, it means that you have diffraction, and typical diffraction effects include diffraction by edges, diffraction by tips or by curved edges, but also the existence of wave species which are not immediately described in optical terms, like, for example, surface waves or leaky waves or lateral waves, which are wave species that we will discuss in the next weeks. Okay, that's all for today. I have taken the initial slides in this lesson from this book by Giuliano Toraldo di Francia, which was an important physicist who studied optics in the University of Florence, by the way. And this book is in Italian. There is also much material taken from this beautiful book by Solimeno, Crosignani, and Di Porto, which is published by Academic Press. This is a quite advanced book on optics, but it contains a wealth of information which I have used for collecting these slides. I think it's everything for today. Next week we will talk about the asymptotic approximation of integrals. Thank you.
Thank you. Bye.
And thank you also for those who are connected via Google Meet. I'm sorry I cannot hear from you. In any case, you will find the recording of this lesson in the usual place, you know. Thank you and see you next week then.
Thank you. Bye.